The geological timescale is a system of dating that classifies geological strata, or layers of rock, in time. The study and dating of rock layers is called stratigraphy. For example, stratigraphers look at the types of fossils that appear at different rock layers, and when the fossil record dramatically changes, for example, when many types of fossils cease appearing at all, it is clear that a mass extinction event occurred. Other evidence found in the geological record can explain why that extinction event occurred, for instance, that an asteroid strike or an ice age took place at that time. The geological timescale is used by Earth scientists to describe the timing and relationships of events in geologic history, or deep time, which is divided into eons, eras, periods, epochs, and ages. Here's a short video about life on Earth in geological time.
The tale of life on Earth has been unfolding for about 4 billion years, and we humans are just the last word on the last page of that story, at least so far. And the vast stretches of time that are covered by the history of life can be hard for us to fathom. We rack our brains trying to imagine what a few hundred years looks like, let alone billions of years. And like speaking for myself, I can't even remember what I had for breakfast this morning. So to help us really appreciate the full expanse of time, scientists have turned to the rocks. By looking at the layers beneath our feet, geologists have been able to identify and describe crucial episodes in life's history, from bursts of evolutionary diversity to disastrous extinction events. These key events of new life and sudden death frame the chapters in the story of life on Earth. And the system that we use to bind all these chapters together is the geologic timescale. First, let's talk about the history of geologic time itself, because figuring out how to read history in rocks was not easy. For much of human history, of course, we had no idea how old the Earth was, or what actually happened in deep time, or what happened in what order. But in 1669, Danish scientist Nicholas Steno published the first laws of stratigraphy, the science of interpreting the strata, or layers of rock, in Earth's outer surface. Steno argued that the layers closer to the surface must be younger than the layers below them. So the farther down you dig, he thought, the older the fossils are that you find there. Sounds legit, right? But in Steno's day, when some people thought that fossils had literally fallen from the sky for some reason, this was a pretty revolutionary idea. Building on Steno's ideas, Italian geologist Giovanni Arduino went a step further and began naming the layers of rock. In the 1760s, Arduino studied the Italian Alps, organizing their layers based on their depth and composition. The lowest layers of metamorphic and volcanic rocks he called their primary layer. Above those were hard sedimentary rocks, which he called secondary, and the top layers of softer alluvial deposits he named tertiary and quaternary. But because rock layers don't appear in this same order all over the world, there is no way for geologists to compare rocks from one location to another. Without a way to compare strata, there could be no universal timescale. Finally, in 1819, English geologist William Smith figured out the solution to this problem: fossils. By comparing the remains of ancient organisms from different rock formations, Smith could match their ages regardless of how far apart they were. For example, Smith realized that fossils of many early species of trilobites are found below ammonite fossils, which are in turn below certain kinds of shellfish. So any place in the world where you find these first trilobites, you know that you're looking at rock that's older than when ammonites lived. And even in the most ancient rocks that have little or no evidence of life, scientists can still look for signs of the very earliest major geologic events, like when continents first formed, and even when the Earth itself cooled and solidified. Thanks to the work of early geologists like Steno, Arduino, and Smith, modern scientists have used these and other clues to create what we now call the geologic timescale, or GTS. The GTS has been reworked many times to reflect the latest knowledge of Earth's history, and today it's organized into 5 subgroups: eons, eras, periods, epochs, and ages. Organizing time in increments like this allows us to ask questions about history on different scales. In the largest increments, like eons and eras, we can ask the biggest of big picture questions, like, was there life on Earth at this time? If there was, what did it look like? Did it live in the water or on land? This is the kind of top-level view we're going to take today. But the smaller increments of time, like periods and epochs, help us take a tighter focus and ask more specific questions, like, what was the climate like during this window of a few million years? And how did life around the world adapt to it? We'll be talking about those in more detail in future episodes when we talk about each era, period by period. Okay, so let's get the biggest of big picture views of Earth's history right now by taking a tour of all the eons and eras in the GTS. Eons are the largest slices of time, ranging from 500 million to nearly 2 billion years long, and the earliest eon is known as the Hadean. It begins with the very formation of the Earth itself, around 4.6 billion years ago, and ends 4 billion years ago. And this is the only eon that doesn't have any fossils, because back then, the world was just hell. Named after the Greek underworld Hades, the Hadean lived up to its name. The planet was racked by volcanic activity, cosmic bombardments, raging storms, and temperatures that were at times hot enough to melt rock. But even in this searing wasteland, life may have been able to form. While no fossils have been found from this eon, small amounts of organic carbon have been discovered in Hadean rocks that some experts think is evidence of the earliest life. These first organisms were tiny and single-celled, but they were eventually able to shape the future of the entire planet. So their appearance is the one major benchmark of this eon. The Hadean was brought to an end by the cooling of the crust of the Earth, setting the stage for the continents to eventually form. And this cooling marked the beginning of the next phase, the Archean eon, which ran from 4 billion to 2.5 billion years ago. Named for the Greek word for origin, the Archean was once thought to be when the first signs of life appeared. But at the very least, it's fair to say it was the first time that life flourished, forming mats of microbes in the primordial seas. The fossils that these microbes left behind are called stromatolites, or sometimes stromatoliths. And the very oldest of them, like those found in Western Australia, date from the Archean. During this time, the atmosphere was mostly carbon dioxide. But the appearance of cyanobacteria was about to change all that. Then, 2.5 billion years ago, the Archean gave way to the Proterozoic eon, meaning earlier life. And around this time, photosynthetic bacteria, along with some multicellular forms of life, spewed tons of oxygen into the atmosphere. This probably wiped out most of the anaerobic life on Earth, but it cleared the path for crucial new organisms, including the ancestral eukaryotes, whose cells each had a nucleus and organelles wrapped up in membranes. Eukaryotes developed into the first really big, complex, and sometimes kinda weird forms of life, such as the frond-like Carnea and the plate-shaped Dickinsonia. These new, larger organisms quickly diversified, and by 541 million years ago, we were at the doorstep of the next and current eon, the Phanerozoic. Its name means visible life, and the Phanerozoic was when life really became obvious. This is the eon that's home to trees, dinosaurs, newts, aardvarks, us humans, basically life as we know it. Whew, how you holding up? You doing okay? We've covered about 3.5 billion years already. Just got another 500 million to go, and then we're home free. Okay, now from here, it's best to explore the Phanerozoic eon through its eras, the next level down in the divisions of time. This will let us explore more recent history in greater detail. The first era of our current eon is the Paleozoic era, which began 541 million years ago. This chapter was defined by the diversification of visible life, and it started with a bang, actually an explosion, the Cambrian explosion. This rapid growth in diversity and complexity in the world's oceans is such a huge deal in the history of life that all the eons that came before it, the Hadean, the Archean, the Proterozoic, they're all collectively known as the Precambrian. At the start of the Paleozoic, over about 25 million years, the fossil record suddenly reveals the appearance of complex animals with mineralized remains. You know, hard parts. Shells, exoskeletons, that kind of thing. And the very first of these new animals to become truly widespread were the trilobites. They were so common all over the world that they've been used as index fossils for the Paleozoic era for centuries, ever since the days of William Smith. But the trilobites soon had competition. Fish developed teeth and jaws and came to dominate the seas, including the first sharks and armored giants known as placoderms. Meanwhile, the land, which had been barren since the formation of continents back in the Archean, was finally being populated. First by plants and then by arthropods. By 370 million years ago, entire ecosystems had developed on primeval continents. Soon after, the earliest amphibians evolved and hauled themselves out of the water, leaving their first vertebrate footprints in the mud. 299 million years ago, the supercontinent of Pangaea had formed, with an enormous desert at its center. This desert was quickly populated by the ancestors of what would eventually become reptiles and mammals, which could thrive in dry conditions, unlike amphibians. But this time of incredible growth couldn't last forever, and instead, the Paleozoic era ended in cataclysm. 252 million years ago, 70% of land vertebrates and 96% of marine species disappeared from the fossil record, including survivors of previous extinctions, like our friends the trilobites. I still miss those guys. The event, known as the Great Dying, was the most severe extinction in our planet's history, but its exact cause is still unclear. A possible meteorite impact off the coast of South America might be one clue, and in Siberia, layers of basalt show that massive volcanic eruptions covered large swaths of Pangaea in lava. Both of these incidents coincided with the end of the Paleozoic, and it seems more than likely that the extinction had many causes. In any case, the Paleozoic may have begun as a chapter defined by an explosion of life, but it ended in nearly absolute death. It took millions of years for life to recover, but when it did, a new world, the Mesozoic era, had arrived. This is often called the Age of Reptiles, and with good reason. Right from the start of the Mesozoic, reptiles were incredibly successful. This is when they took some of their most famous forms, like dinosaurs, pterosaurs, and a variety of marine species. In fact, all of the non-avian dinosaurs lived only in the Mesozoic, so they remain one of the best index fossils of this era. And many modern groups of organisms also evolved in the shadows of the reptiles, like mammals, frogs, bees, and flowering plants. But the Mesozoic era came to an end 66 million years ago, with yet another episode of devastation. This time known as the Cretaceous Paleogene, or KPG, extinction event. Like all mass die-offs, the KPG had many causes, but probably the biggest of them was a giant asteroid that struck the Earth, sending enormous amounts of ash into the atmosphere, blocking out sunlight, and creating a vicious cold snap across the planet. Without the sun's energy, entire plant communities died, and the animals that relied on those plants perished with them. Evidence of this impact can be found in a layer of iridium in rocks dating to the end of the Mesozoic. Iridium is an element that's rare on Earth, but very common in asteroids and comets. And a giant impact crater in the Gulf of Mexico, whose age matches the date of this extinction, has become the smoking gun for the asteroid hypothesis. The victims of the KPG extinction were some of the biggest reptiles of the land, sea, and sky, including all of what we now call the non-avian dinosaurs. Birds, of course, survived the cataclysm, making them the last surviving lineage of the dinosaurs. Okay, we have 66 million years to go, and that's the last major extinction event that we have to talk about. I thought you might want to freshen up, so I bought these pre-moistened towelettes. It's going to... You have some iridium here on this side, on your forehead, other side. With all the great reptiles gone, the smaller animals that remained were able to eke out a living in the next era, the Cenozoic. This is our era, in more ways than one. It's the era that we're in today, and it also marks the rise of the mammals. Soon after the KPG extinction, the climate warmed, and jungles stretched across the planet. Mammals quickly recovered in this hothouse world, and by 40 million years ago, most of the mammal groups that we recognize had come about, like whales, bats, rodents, and primates. But starting around 34 million years ago, the climate began to shift again. This time, ice caps started to grow at the poles, taking up much of the planet's water. And these drier conditions created a new habitat, the grassland, where ancestral horses and antelope were hunted by the first cats and dogs. It was also in these grassy plains, 7 million years ago, that a species of ape called Sahelanthropus became the first known primate to walk upright. 2.6 million years ago, the ice caps expanded even more, and the Earth entered a glacial period. This is the one you hear referred to as the Ice Age. Over the course of these last several million years, most modern life forms that we know about developed and thrived, alongside giants like mammoths, ground sloths, and saber-toothed cats. Once again, though, this era of diversity came to a morbid end. Starting around 15,000 years ago, the climate began to warm up, and over the next few thousand years, many of the giant fauna went extinct. By 11,700 years ago, the last major glaciation was over, and modern humans inhabited nearly all the corners of the globe. But how big a role we played in the extinction of the so-called Ice Age megafauna is hotly debated. Regardless, there's no escaping the fact that our species has shaped the Earth to its will since then. Like cyanobacteria and the dinosaurs before us, we've had a huge impact on habitats, other organisms, and the biosphere itself. And as we've learned today, it's the most dominant forms of life that define each phase of deep time. So even though our time on this planet amounts to the last word on the last page of the story of life, we are the authors of the next chapter. One day, the epoch of humans may be detected by the marks we make on the land, the traces of our cities and farms. And our very bodies will be the index fossils of this time. No matter how our chapter ends, we get to be characters in a truly amazing story.
At the end of the video that you just saw, the geologist refers to the epoch of the humans. In using this term, he is gesturing towards the fact that, although officially we are still living in the epoch called the Holocene, since the year 2000, geologists have heatedly debated whether we have in fact left the Holocene and entered a new geological epoch that they are naming the Anthropocene. Although some people translate Anthropocene as Age of Man, in fact, the Greek word for man is andros, whereas anthropos, the root of anthropology, refers to the human. Thus, the correct translation of Anthropocene is the epoch of the human. Let's listen to a 2010 talk by Will Stephan, one of the leading geologists, who argues that we have left the Holocene and are now in an era that he advocates for naming the Anthropocene.
Thanks very much, Steve. For those of you expecting a talk on climate change, actually, thankfully, you won't get it. I'm going to talk about this rather broader context, broader term, which puts climate change in a much broader context. That's the term of the Anthropocene. Now, for those of you who've studied geology or even watched Hollywood films, you know that geologists like to look at Earth history in terms of periods, eras or epochs or something. You've probably heard of the Pleistocene, many of you. Those of you who've seen a famous Hollywood film certainly know the Jurassic era, Jurassic Park. But there's a group of us now who are proposing that the Earth has actually entered a new epoch, at least, perhaps even a new era, which is a more substantive term, and that is the Anthropocene. And as the name indicates, anthropo refers to us, refers to human beings. So unlike the previous eras in Earth's history, which were marked by meteorite strikes, big changes, for example, in plate tectonics or something like this, this is a biological species, ourselves. And we are pushing the planet into a new and perhaps somewhat frightening geological as well as biological era. So let's get started with what the Anthropocene actually means. I really like to show this graph up here. This is some data taken from an ice core in Antarctica, the famous Vostok ice core. That's a Russian station by the name of it, but many people don't know this ice core comes from Australian territory. This is from the 42% of Antarctica which we claim. Now, this particular record goes back nearly 500,000 years. The red line in the middle is a proxy for temperature, how temperature changes through time. The top graph, the blue one, is the famous greenhouse gas that we're all concerned about, carbon dioxide. The bottom one is methane. The important thing is entire human history is encompassed in this ice core. Fully modern humans, Homo sapiens, evolved around 250,000 years ago. You see that in the middle. We evolved in Africa. Now, for well over 90% of our time on the planet, you see that stretched out, we were hunter-gatherers only. Our genetic code is wired for hunting and gathering and living in small groups of up to 200 or 300 people. We live in a quite different world. The beginning of agriculture only occurred at the very end of the record, at a warm period. Notice how the Earth oscillates in a beautiful rhythmic pattern, much like a human heartbeat, between long cold periods and short warm periods. But the present warm period is unusually long. I'll get to that in a moment, which means that it's given us a bit of time to break out of the hunter-gatherer mold. It's only during this last 10,000 years that we've had agriculture and so on. Let's look at that in a little bit more detail. This is another ice core, and this comes from the opposite end of the planet. That other one was down here in the south in Antarctica. This one comes from Greenland, up not far from the North Pole. And it's actually a much shorter time period. It's the last 100,000 years. So it captures the Earth as the temperature, and this blue line is another proxy for temperature, as it's sliding into the most recent ice age. And there are a lot of spikes that you see in the northern hemisphere that you don't see so clearly in the southern hemisphere, but we won't be concerned about those here. We're looking at common trends across the Earth. Now we unpack what has happened to us as a species in more detail. The first successful migration of fully modern humans out of Africa was about 85,000 years ago. And you see that there was a dip in temperature, which means that sea levels dropped. It was easier for humans to migrate out of Africa, and they did. And they went around the Arabian Peninsula, moved on through around the Indian subcontinent, through the Indonesian archipelago. The Earth was getting even colder through that time. Sea level was dropping even further. We were connected to New Guinea. Tasmania was connected to the mainland, and so on. And the first wave of fully modern humans ended up here. In fact, it branched at the very end between New Guinea and Australia. So indigenous Australians are the end point of the first wave of fully modern humans out of Africa. They left groups of people all the way along in the Indian subcontinent and so on. Now, some of those later on then sent migrations up from South Asia into Europe. Now, those of us of European descent, and I'm primarily of European descent, I can trace my mitochondrial DNA. In fact, I can trace mine back to that second red arrow about 33,000 years ago. But I come from South Asia originally. So basically, all of us who are Europeans come originally from South Asia and originally from Africa. But again, look at this ice core record. About 10,000 years ago, the Earth became very much steadier in climate. It was warmer, carbon dioxide was much higher, plants were growing better. Sea levels are rising too, starting to isolate us again, as the sea level rose by 120 meters between the bottom of the ice age and that period there. Now, the geologists actually have a name for that 10,000-year period where the blue line hits zero, which is simply a reference temperature, and it stays there pretty steadily. That's called the Holocene. So that's still the official epoch that the Earth is in. We're suggesting now that we're moving out of that epoch, out of the Holocene and into the Anthropocene. Okay, well, what has happened during that 10,000-year period of unusual warmth and reasonably steady climate, although rainfall has gone up and down through that period? Well, first of all, about 10,000 years ago, we saw the beginning of agriculture. Very interestingly, it appeared pretty much simultaneously at 4 different places on the planet. Most people associate it with the Middle East, with present-day Syria, Mesopotamia, and so on. That was one of the places. But one of the other places was just next door to us, and that was New Guinea. The New Guineans also invented agriculture about 10,000 years ago. The other 2 were in the Americas, in Mesoamerica and up along the east coast of North America, pretty much simultaneously. Then we started living in villages because we had a food supply. We grew towns and cities. We developed civilizations in Africa, like in Zimbabwe, in the Americas, and of course, the ones we study in school in Europe, like the Romans and so on, and the Greeks before them. So all of this occurred in this unusually warm and stable 10,000-year period. Now, are we set to go into the next ice age? Absolutely not. By a quirk of the Earth's orbit around the sun, this nice, steady period of 10,000 years will stretch to at least 20 and perhaps 30,000 years if we don't interfere with it. So humanity is really set for a very long period of equable climate on the planet in which to further develop. However, this is where the Anthropocene comes in. Let's see what's been happening. We have been changing remarkably through this 10,000-year period, but something different happened around 1750 to 1800. Now, we've always affected the environment. In fact, there's some evidence that indigenous Australians, as well as Asians and so on, led to the extinctions of some very big fauna, giant kangaroos, wombats in our case, woolly mammoths and so on in Asia. And there's still debate in the scientific community, but there may be a human imprint there. We certainly learned to use fire and modified landscapes. But we basically relied on our own energy and the energy of animals that we might be able to use, and a little bit of wind and water. But around 1750 or 1800, something new occurred. We were able to access fossilized energy that had been built up over millions of years under the surface of the Earth. Coal, petroleum products, gas, and so on. That led to an absolute unleashing of what we call a human enterprise. So what we tried to do here is to look at the human enterprise from 1750 to pretty much the present, and look at several different aspects. Look at population, going from less than 1 billion up to between 6 and 7 billion now. Total real GDP, direct foreign investment, they capture aspects of the economy. Damming of rivers, water use, fertilizer, these are resource uses. Look how the values are going up and up and up in each of those. Urban population going up, paper consumption. We had to have an indicator for globalization. And what better? Well, we heard a bit about Coca-Cola. That would have been a pretty good one, too. But we went for McDonald's restaurants. And there you see, in terms of the numbers, thousands of McDonald's restaurants around the world. And then we look at transport and communication. There's motor vehicles. We all live with motor cars. We accept them as normal. There were virtually none before 1950 around the world. Communications, telephones, that's landlines. They're disappearing now in favor of mobile phones. International tourism. Now, notice something remarkable about those graphs, and that's the year 1950. A second event happened in 1950. Well, it was, as you probably know, the Second World War, which not only knocked off quite a few people, although you don't see much of a blip in the population. What it did do was break down old institutions, particularly economic institutions, old ways of thinking, and it led to a massive increase in connectivity, networking, financially, information flows, and so on. And that led to what we call the Great Acceleration, the period from 1950 to the present. Some of the things we take for granted, foreign direct investment. We just heard that 25% of our mortgage money is actually brought in from overseas. We are tightly linked with the global financial system, as we found out. But look at international tourism. Look at motor cars. Look at McDonald's restaurants. They virtually didn't exist before 1950. So we've seen a massive change in the way we organize ourselves, in the way we live since 1950. So those of us who are studying the Anthropocene say that the beginning was probably around 1750 to 1800 when we started accessing this new energy source, fossil fuels. But stage 2 of the Anthropocene started in 1950. When we reorganized ourselves, population exploded, economy exploded, resource use exploded, and so on. Well, why do we say this is really a new geological epoch? You actually have to prove that this is doing something to the Earth. And indeed we do. So in the very same scale, from 1750 to 2000, we look at what's happening to planet Earth. The top 3 graphs are the famous greenhouse gases. The one in the upper left is carbon dioxide. And I showed you that elegant Vostok ice core of CO2 going up and down. During the time we've been on the planet, it's oscillated between 180 and 280, and it's maxed out at 300 parts per million. It is now 387.2, I believe, parts per million, and going up at about 2 parts per million per year, unprecedented in the geological record. There's nitrous oxide, methane, two other greenhouse gases, depletion of ozone in the stratosphere, rocketing up again since 1950, new chemical compounds. These next two, Northern Hemisphere surface temperature and great floods, are the only two climate ones on this set of 12. So that captures climate change. But look at direct human impact on ocean ecosystems, coastal zone, coastal biogeochemistry. That's nitrogen flowing through the coastal zone. Look at the massive change to the nitrogen cycle. You see 1950 again appearing there. And direct impact on land, loss of tropical forest and woodland, again going up. Amount of domesticated land, that's land that has been completely made over and used for crop, plantation, forestry, and so on, again going up. Biodiversity, the extinction rate, shooting up again. So, this is strong evidence that we have left the Holocene. In each case, except perhaps yet for temperature, we have left that envelope of environmental stability which typifies the Holocene. Now, this is the case we're putting forward to the Geological Society of London, which is the body that actually decides what era or epoch in Earth history we are in. And they formed a working group that's studying this now. And you may find in a couple of years that there will be an announcement made that the Earth has officially left the Holocene and entered the Anthropocene. This is some of the evidence we're putting forward. Interestingly, climate change isn't the strongest argument. The strongest argument is biodiversity. Why is that so? Many of the Earth's epochs are defined by sharp changes in the fossil record. Something happened to the biology of the planet. A classic example, when the dinosaurs went extinct relatively rapidly. Now, it's thought that that was caused by a meteorite strike on the planet and so on. But in many cases, periods of the Earth's history are defined by abrupt changes in the biological part of the planet. We're seeing it now. Extinction rates are 100 to 1,000 times background level. And that's due to us, of course. And that masks even more changes in terms of moving species around the planet, range contractions of many species who aren't extinct yet, but they're functionally extinct, and so on. That's expected to increase by another factor of 10 this century as climate starts to shift. Well, what do we do about this? Do we accept the Anthropocene and try to live in it? Or can we recover the Holocene in some way or another? And this brings me to the last point I want to make. There's a group of us who published a paper in Nature a couple of years ago, about a year and a half ago, and we're proposing something that we call planetary boundaries. It's a very simple concept. We all understand boundaries. This bloke here obviously has a boundary right behind him. He doesn't want to step across that because it won't be very good for him. And he has to respect that. We teach our children boundaries. We don't let them play on busy streets. We keep them away from other dangerous things. We accept boundaries as important parts of our life. But we don't do that yet at the planetary scale. So we think it's time to start thinking about planetary boundaries. Well, how might you define planetary boundaries? Well, what we attempted to do was to look at how the planetary system actually works. How does our environment function? Where are parts of the planetary environment that could shift, perhaps even shift abruptly or irreversibly if we push them too hard, if human activity pushes them too hard? Now, we can look at the ice cores and we can look at other so-called paleo evidence, and it gives us some really good clues because back in the Earth's history, we've seen abrupt shifts, and we're starting to get an inkling of why those abrupt shifts occurred. And we may be pushing the planet towards some of those, which would not be healthy at all for Homo sapiens or for our societies. We think we've defined, at least initially, 9 processes or parts of the Earth's system that we need to respect. One of them, only one out of the 9, is climate change. And what's our control variable there? Well, we chose carbon dioxide. And we believe from examining all the evidence of the past, we shouldn't go above 350 parts per million CO2 to stay within a safe Holocene type environment. I just mentioned where we are now, 387.2. We're in overshoot. 2 others we believe we're in overshoot. One of them is the nitrogen cycle. We actually now fix more nitrogen. By fix, I mean pulling nitrogen out of the atmosphere, unreactive nitrogen, and through industrial processes, turning it into reactive nitrogen, spreading it across landscapes. We need it, of course, to grow food. But the food actually takes up a small percentage. The rest of it moves out as pollution, polluting groundwater, polluting the atmosphere, polluting coastal seas. Third one is the one I mentioned, rate of biodiversity loss. But there are other important things too. Ozone depletion, aerosol loading, that's pollution. How far should we go there? We're acidifying the ocean. Where should the boundary be there? Global freshwater use. We're using nearly half of the water now that flows to the ocean. There's not much left for the rest of the species on the planet. Where should we draw the line? What defines a Holocene environment? So I think this is one of the most active areas of research. We're only beginning to understand where we should try to put boundaries. But we believe it's an important concept because once you define where the boundaries are, then it defines a safe operating space where humanity can maneuver. We can talk about equity issues, we can talk about economic growth and so on. But we are biological species and we live on a planet and we need to respect the boundaries that the planet itself intrinsically sets for us. So in summary, we have moved into the Anthropocene. Whether we should stay there is a decision we should talk about as a global community. Because I think in the end, the risks associated with the Anthropocene will really push us past some limits. And like those earlier civilizations I showed you on the first slide, there is no guarantee civilization lasts forever. The Romans aren't around, nor are the Mayans. And we might not be either, unless we start thinking globally as well as locally. Thank you very much.
For geologists to determine that a new epoch has begun, there must be enough stratigraphic evidence to do so. That is, we must be able to imagine that future geologists, who might no longer be human geologists, existing millions or billions of years in the future, could look back at the rock layers from this period in time, and they would see that major shifts had occurred on the planet. Why contemporary geologists increasingly concur that we are in fact in a new epoch is because they believe that their future counterparts would indeed see many things in the rock record for this period that are indicative of planetary change. They would be able to see evidence that the climate had warmed and that the oceans had risen, for example. And they would be able to see that there had been a dramatic loss in biodiversity, which some are arguing is the sixth great extinction in Earth's history, which will mean major changes in the fossil record. Also importantly, future geologists would see a lot of a new substance in the rock record, something never seen at any of the previous strata: plastic. More specifically, they would see plastiglomerates, plastic rock, or plastic sediment hybrids. While plastic biodegrades over thousands of years, a blink of the eye in terms of deep time, when buried under sediment and thus protected from ultraviolet rays, their lifespan will be considerably longer. Today, microplastics are already found everywhere on Earth, in the ice of the Arctic, in the sand on the most remote desert islands, to the deepest floors of the sea. Geologists have also noted that debris from the detonation of atomic bombs in the 20th century will also be visible in the rock layer from this time, and so one more stratigraphic trace that humans will leave are the remnants of our war. Climate change, the current rate of biodiversity loss, plastiglomerates, and traces of atomic bombs are all anthropogenic markers, or markers caused by humans, that will exist for millions or billions of years in the geological record. Thus, future geologists would be able to read from the rock record that humans were a dominant species and that we dramatically changed our world. This is why an increasing number of Earth scientists are calling the current epoch the Anthropocene. If we agree that we are today living in the Anthropocene, it still remains to be asked, how long ago did this epoch begin? As it turns out, this is a complicated question, both from geological and political perspectives. Different human impacts on Earth can be seen in the rock record at different points in time, and the impacts we choose to emphasize by dating the epoch to that moment will have different political implications. In her best-selling book, The Sixth Extinction, journalist Elizabeth Kolbert argues that the Anthropocene began when humans killed off the Ice Age megafauna, as well as, she believes, archaic forms of humans, such as the Neanderthals. We can see the mass die-offs of the Pleistocene or Ice Age megafauna in the geological fossil record, and so dating the age of the human to the very beginning of human history is an option, but only if we buy into the hypothesis that modern humans were responsible for the extinction of the Ice Age megafauna, a topic that is still hotly debated. If there were consensus on this matter, dating the Anthropocene to the Ice Age megafauna extinction is the most depoliticizing of options, since few people today are going to get up in arms about the demise of the saber-toothed tiger or the woolly mammoth. And in tracing the start of the Anthropocene to the earliest days of Homo sapiens, Colbert essentializes the species as environmentally destructive, even hypothesizing that Homo sapiens have a destructive gene, which is what marked us off from the other types of humans that, according to Colbert, Homo sapiens both mated with and annihilated, and whose genomes we later mapped. Like Colbert, some scientists have argued for dates in the remote past as the start of the Anthropocene, such as the beginning of agriculture 12,000 years ago, since even in its earliest forms, agriculture resulted in a disruption of ecosystems, species extinctions, and biodiversity loss. This date, however, would make the Anthropocene synonymous with the Holocene, or would simply be a renaming of the Holocene. Geologists have also proposed far more recent dates for the start of the Anthropocene, however. These include 1. The Columbian Exchange, and specifically the start date of 1610, when the CO2 dip caused by the conquest of the Americas reached its lowest point and resulted in a little ice age. 2. The Industrial Revolution in Europe and America, and especially the beginning of the use of fossil fuels and invention of the steam engine in the second half of the 18th century, followed by a great acceleration in capitalist industrialization that occurred after World War II. This is the time period stressed by Will Steffen in his lecture. The specific start date chosen within this time frame is 1780 for the invention of the steam engine. 3. And finally, July 16th, 1945, when American scientists detonated the first nuclear bomb at a military test facility in the desert of New Mexico, a few weeks before the Americans dropped atomic bombs on Hiroshima and Nagasaki on August 6th and 9th, 1945. Two Earth scientists, Simon Lewis and Mark Maslin, are responsible for proposing the Columbian Exchange as the start of the Anthropocene, and the date of 1610 in particular. They observe that the near extinction of indigenous people in the Americas due to European diseases, as well as war and enslavement, resulted in a massive population drop between 1492 and the mid-17th century, and that there were between 54 and 61 million indigenous people in the Americas in 1492, and as few as 6 million remained by 1650. This genocide had, as a consequence, a, quote, near cessation of farming and reduction in fire use in the Americas, which Lewis and Maslin observe
resulted in the regeneration of over 50 million hectares of forest, woody savanna, and grassland, with a carbon uptake by vegetation and soils estimated at 5 to 40 petagrams within 100 years. The approximate magnitude and timing of carbon sequestration suggest that this event significantly contributed to the observed decline in atmospheric CO2. Between 1570 and 1620, documented in 2 high-resolution Antarctic ice core records. This dip in atmospheric CO2 is the most prominent feature, in terms of both rate of change and magnitude, in pre-industrial atmospheric CO2 records over the past 2,000 years.
1610 is the date within the Little Ice Age of 1594 to 1677, when atmospheric CO2 dipped to its lowest point as a result of the Columbian Exchange. This was, in Lewis and Maslin's words,
a relatively synchronous global event noted in geologic deposits worldwide.
In addition to the CO2 dip, Lewis and Maslin observe that there are other stratigraphic indicators that support the choice of this time period for dating the Anthropocene, including
decreases in atmospheric methane, enrichment of methane, and decreases in carbon monoxide in Antarctic ice cores, pollen in lacustrine sediments showing vegetation regeneration, proxies indicating anomalous Arctic sea ice extent,
and significantly, the homogenization of biota around the globe. Thus, Lewis and Maslin make a strong case for choosing 1610 as the start of the Anthropocene, but they also acknowledge that an equally strong case can be made for the Industrial Revolution and great acceleration in industrialization in the mid-20th century, while the Columbian Exchange resulted in a dip in carbon emissions and consequently cooling temperatures. Industrialization in more recent centuries has caused an increase in carbon emissions and a warming of the planet, while the Columbian Exchange began the process of homogenizing biota around the world and biodiversity loss. These processes have been accelerated in the 18th through 20th centuries, with wild animals around the planet being driven to extinction in favor of a small number of biota that humans breed and cultivate. These biota are the agricultural animals of humans and the crops that we feed them. In addition to these arguments for dating the Anthropocene to the 20th century, there is, of course, the explosion in the production of plastic. Finally, the July 16, 1945 date is a candidate for the start of the Anthropocene, since radionuclide fallout from atomic bomb testing have become part of the stratigraphic record. Although Lewis and Maslin see the 1945 date as the weakest of the three candidates for an epoch-changing event, it is the date for which the International Anthropocene Working Group has advocated. With so many options for dating the Anthropocene, how should we, or the geologists, decide? Although they are scientists, Lewis and Maslin interestingly argue that what might be the deciding factor in choosing between these dates is politics. Choosing the Columbian Exchange would stress colonization as the cause of the Anthropocene, whereas choosing the Industrial Revolution would stress technological invention and capitalism, while choosing 1945 would stress war. Although Europeans and Euro-Americans are to blame in any of these scenarios, we still need to ask which of these three catastrophes do we want to draw attention to in dating this epoch? Which do we most want to condemn for the human, animal, and environmental devastation that ensued? In an article titled Decolonizing the Anthropocene, Métis anthropologist and Indigenous Studies scholar Zoe Todd and her co-author, art historian Heather Davis, have advocated for choosing the Columbian Exchange date, the date that stresses colonization. University of Alberta Native Studies scholar Kim Tallbear has echoed their argument, noting that for Indigenous peoples in the Americas, the apocalypse began at this time, and what is happening since the mid-20th century is simply that the apocalypse is beginning to detrimentally impact white people after centuries of their profiting from it. For Todd, Davis, and Tallbear, dating the Anthropocene to the 18th to 20th centuries reflects a racist white or settler colonial worldview, one that privileges the point at which the apocalypse began to take forms that would ultimately threaten Europeans and settlers, rather than the earlier date at which it nearly annihilated Indigenous people in the Americas. Despite these arguments, by and large, white male scientists and white settler academics who have dominated Anthropocene discourses have adopted 18th to mid-20th century dates, and hence it is more common to blame capitalism than colonialism as the cause of the Anthropocene. As environmental historians show in works such as The Shock of the Anthropocene, although we like to believe that we only learned about climate change recently, and that by the time we did so, it was already more or less too late, in actual fact, European scientists recognized centuries ago that human activity could impact the climate. If we date the Anthropocene to the Industrial Revolution, it can be said that at least some humans have known since the start of this epoch that they were changing the planet's climate, which inevitably would impact its biota. These scientists anticipated anthropogenic climate change to be a good thing, however, at least for white people. A warmer planet would suit us, they thought. We could farm further north and have a longer farming season, and we don't like the cold anyway. But of course, these were people living in cooler European countries. People in southern parts of the globe don't want a warmer climate. For them, climate change means drought and famine, a shorter farming season. For indigenous people in the north, global warming means the melting of permafrost on which their communities are built. And for people on low-lying islands, it means their countries being submerged in the sea. One way in which the Anthropocene is socially unjust is that those who have done the least to cause this epochal shift, whether non-human species or the most vulnerable of our own species, are those who are being hurt the first and the most acutely. The planet is warming most quickly in the far north and south, and thus it impacts the Inuit and the least developed nations, the Arctic animals and the animals from the southern parts of the globe, the hardest. In contrast, those who are most responsible for climate change, Europeans and Americans, are living in more temperate zones and, for the time being, and with some exceptions, are safely above sea levels. While white Europeans and settlers are now being impacted, these are not the people who have borne the brunt of anthropogenic climate change. Another question that scholars have raised with respect to discourses on the Anthropocene is whether we should even be calling this epoch the Anthropocene, the age of humans. This name is both too narrow or anthropocentric, since all of life on Earth is impacted by the planetary shifts that are occurring, and it is narcissistic and part of the problem to focus our attention on the human, as this name does. At the same time, this name is too broad, for it suggests that all humans are equally responsible for the environmental changes that are happening, or that it is the species Homo sapiens itself that is a problem, rather than a small subset of that species. Some social justice scholars have thus argued that we should actually be calling this epoch the Eurocene, the white supremacy scene, the plantation scene, the Androcene, or the capital scene, in order to stress the ways that it is really white people, colonialism, men, the Columbian Exchange, including the transatlantic slave trade, and capitalism that have caused the environmental changes that we are now experiencing. Feminist geologist Jill Schneiderman has proposed the name Pleistocene, which means the age of the least new life, in contrast to the Pleistocene, which is the age of the most new life. As with another term that has been proposed, the Homogenocene, Pleistocene would be a less humanistic name for the time period, since it shines a light on the impacts of human activity rather than on humans themselves, and this impact is first and foremost a massive loss in biodiversity on Earth. Other proposals for naming this epoch include the Pleistocene, since, as was discussed earlier, one way that humans will be seen in the sedimentary record long after we as a species are extinct is through the plastoglomerates that we will have left behind, or the plastosphere that we have created. Plastic has been described by Heather Davis as the toxic progeny of humans, progeny that will immortalize us. Although some scholars have argued that naming this epoch the Anthropocene results in a human turn in theory or a new humanism, others have asked, what does the Anthropocene say about the relationship of humankind to nature? Some discussions of the Anthropocene gloat over how powerful the Anthropocene demonstrates humans to be and take it as proof of human exceptionalism. For example, Elizabeth Kolbert concludes the sixth extinction by arguing, at the risk of sounding anti-human, whether or not humans survive the Anthropocene is not in the end what's most worth attending to. Right now, in the amazing moment that to us counts as the present, we are deciding, without quite meaning to, which evolutionary pathways will remain open and which will remain forever closed. No other creature has ever managed this. This is a strange passage, although it begins with a kind of anti-humanism, when Colbert states that whether humans survive or not is not what is most important. It also expresses a humanistic awe at how unique and impressive humans are. We are deciding the future of life on Earth, and no other creature has ever managed this. The implication seems to be that this huge responsibility that we have at this moment in time of deciding which evolutionary pathways will remain open and which will remain forever closed is what is really important, what should capture our attention and our efforts, not the project of our own individual survival as a species. But what is Colbert suggesting? That we should engage in a calculation or evaluation of which species we want to survive the Anthropocene and which we don't care about? That we should try to engineer things such that it isn't giant rats and plastic-eating bacteria that take over the planet, as seems most likely, but rather some other kinds of species that we find more appealing or charismatic, such as koalas and dolphins, regardless of whether we're here to see them. We see in this passage a strange kind of exaltation of the human mixed with dismay, which is common in writings about the Anthropocene. Some authors have even written of the good Anthropocene, seeing it as an opportunity to geoengineer the planet in ways that will be positive. Very often, the Anthropocene is taken as impressive evidence of our power and singularity as human beings. As Colbert puts it, we have done something that no other creature has managed to do. This human exceptionalism is not quite true, however. In fact, it is very likely that the first mass extinction in Earth's history was caused by moss. According to Colbert's own description of the original Great Extinction event, it occurred when moss grew all over the planet, lowering carbon emissions and leading to glaciation. As she writes, one theory has it that the glaciation was produced by the early mosses that colonized the land and in so doing helped draw carbon dioxide out of the air. If this is the case, the first mass extinction was caused by plants. Close quote. Surely, this is a major blow to human exceptionalism with respect to the Anthropocene. Moreover, the language of deciding that Colbert uses in concluding her book is probably wrong. Colbert herself shows that we have done what we have done without quite meaning to, and so we might ask, have we decided any of this, or is it not rather a big mess that we didn't intend and that we cannot actually get ourselves out of? If we got into this mess without intending to, why should we be so confident that we can decide what comes out of it? While Colbert seems to suggest that even at this point in time, we can choose what evolutionary pathways will remain open and which will not. Her own book suggests that this is not the case. The sixth extinction describes drastic efforts on the parts of humans to save endangered species, such as frogs, bats, rhinos, and a Hawaiian crow, most of which attempts have been unsuccessful. It seems that, as often as not, humans cannot even save the animal species we most prize. And even Colbert seems to suggest that we may not be able to save ourselves. Shouldn't this humble us rather than impress us? Should we perhaps learn from this not to interfere with nature, rather than be inspired to interfere even more, attempting to engineer which evolutionary pathways will stay open in the Anthropocene and to geoengineer the planet itself?